So far you have studied that sound is a form of energy and produces sensation of hearing in our ears. The energy which it transfers from particle to particle is the mechanical energy. But for this transference, the sound needs a medium for its propagation. It requires a vibrating body and a receptor. In the absence of these three, sound cannot propagate. So, these are the requirements for sound to travel. But in order to consider any substance, a medium, there are some requisites, and the requisites are the medium should have inertia, it should have elasticity, and it should be frictionless. Then you were taught that there are two types of waves. For mechanical waves, there are two types of wave motion. One is the longitudinal wave and the other one is the transverse wave. In longitudinal waves, the particles oscillate along the direction of propagation of the wave, while in the transverse wave, the particles oscillate perpendicular to the direction of propagation of the wave. So this is a huge difference between the two. Longitudinal waves consist of compressions and rarefactions, while transverse wave consists of crests and troughs. Compression and rarefaction are the regions where you will observe variation in pressure and density and as well as volume. No such thing happens in case of transverse wave. There is no change in the volume, density or pressure of the medium. Longitudinal waves can travel through all the three states of matter: solids, liquids and gases. But transverse wave travel only through solids and on the surface of water. These were the topics or subtopics that we did so far. And now we will continue after this and we will start with wave characteristics. A wave can be described completely by the terms wavelength, amplitude, time period, frequency, and wave velocity. We will take the example of a longitudinal wave to understand the meaning of these terms. A graphical representation of a longitudinal wave is shown in the figure. The first wave starts with the point A, which is the equilibrium position, and after going through the compression at B and rarefaction at D, it returns to the equilibrium position E. Thus, positions A, B, C, D and E represent one complete wave. The next wave starts from E and goes up to point I. Thus, this figure shows two complete waves. We will refer the same graph in order to understand all the wave characteristics. The first one being the wavelength. The wave begins at point A and ends at point E. Therefore, the wave from A to E, that means the distance between A and E is one wavelength. Also, the points B and F, which represents two adjacent compressions, the distance between B and F is also one wavelength. At the same time, the points D and H are two adjacent rarefactions, and hence the distance between D and H is also considered as wavelength. Therefore, in simple words, the length of one complete wave is termed as wavelength. However, apart from this definition, there are two more definitions that can be written, and that is the distance between two consecutive compressions and or rarefactions. Similarly, distance between one compression and one rarefaction is termed as wavelength. The SI unit of measuring wavelength is meter, but sometimes centimeter is also used. But centimeter is not the SI unit, it is the CGS unit of wavelength. The symbol of wavelength is lambda, denoted by the Greek letter. When a wave passes through a medium, the particles of the medium get displaced temporarily from their original undisturbed positions. The maximum displacement of the particles of the medium from their original positions when a wave passes through the medium is known as the amplitude. So basically, amplitude describes the size of the wave. From this graph, BP, the distance BP is the amplitude of the wave, as well as the distance QD is also amplitude of the wave. One thing to be noted is that the distance BP is equal to distance QD. For the second wave, which starts from point E and ends at point I, as from the given graph, it is very much clear that FR is the amplitude as well as SH distance is also the amplitude, and both of these distances are equal to the amplitude QD of the first wave as well as amplitude BP. The SI unit of amplitude is meter. However, sometimes the other unit of amplitude, centimeter, is also used. The time required to produce one complete wave or cycle is known as the time period of the wave. Now, one complete wave is produced by one full vibration of the vibrating body. So another definition for time period is the time taken to complete one vibration. Therefore, we can say that one vibration is equal to one time period. The SI unit of time period is second. From this particular graph, it is clearly mentioned the time period. How do you define time period in a graph? So for one complete wave, the time taken by one complete wave is known as its time period. The term frequency tells us the rate at which the waves are produced by their source. The number of complete waves or cycles produced in 1 second is called frequency. The SI unit of frequency is Hertz, and 1 Hertz is equal to 1 vibration per second. There is a definite relationship between time period and frequency, and that is that time period is reciprocal of frequency, or we can say that frequency is reciprocal of the time period, and hence another unit of frequency is per second. Therefore, 1 Hertz is equal to 1 per second. Wave velocity is the last wave characteristics. It is defined as the distance traveled by a wave in 1 second, and its unit is meter per second, which is the SI unit. The symbol is V. It is basically written as small v. And the formula for wave velocity is wavelength upon time period. As we all know that velocity in general is given as displacement upon time. So here wavelength is basically the distance traveled by one single wave. So that is why it is the distance factor called wavelength in wave motion divided by time period. That means the time taken by one complete wave. Since we know that time period is equal to 1 upon frequency, time period and frequency are reciprocal to each other. And therefore, on substituting the value of time period over here, we can write velocity as lambda into f. That is the wave equation. This wave velocity formula or wave equation applies to both mechanical as well as electromagnetic wave. I will show you a simulation to make you understand the relationship between frequency and wavelength and how frequency and wavelength affect the wave velocity of the wave. I have taken here a string which when oscillates it produces a or it creates a transverse wave that I have said just now, that now we will see how frequency affects the wavelength. At the bottom you can see a few sliders. Ignore the damping and the tension slider because we will not change the values of tension on this string, as well as we have taken damping to be 0. That means the losses due to friction present in the air or the medium has been ignored. So damping and tension slider is none of our concern right now. Rest of the two sliders, the first one is that of an amplitude. We can change the amplitude of the wave by changing the values that are mentioned here. And similarly, the second slider, this is of a frequency slider. It gives us control over frequency. The unit in which the frequency has been measured is hertz. We will first of all begin with a slider of lower frequency. That means let's turn the frequency slider to a low frequency value and let's see what happens. A low frequency wave is created and very few number of waves are produced. Now, if I shift the slider to the high frequency, then you can see the number of waves per second has increased. Now, higher the frequency, the shorter is the wavelength. On the other hand, the lower is the frequency, the longer is the wavelength. I hope you remember wavelength is nothing but the distance between two crests or two troughs in case of a transverse wave. So on reducing the on reducing the frequency, the wavelength increases, while on increasing the frequency, the wavelength decreases. That means high frequency waves are shorter waves, while low frequency waves are longer waves. The next step is to measure the wavelength of the wave. So for measuring the wavelength of the wave, which is transverse in nature, I will measure the distance between two crests or two troughs. And for that, I need a ruler. So on enabling the ruler option, I get this ruler over here, and first of all, I will try to find out the least count of this ruler. We can find the least count by a formula which you have been taught. On this ruler, you can see the first division, which is 0, and 0 centimeter till 1 centimeter, there are overall 5 divisions. That means the value of each small division is 0.2 centimeter. So 0.2 centimeter, 0.4 centimeter, 0.6 centimeter, 0.8 centimeter, and this is 1 centimeter. After this, it is 1.2, 1.4, 1.6, 1.8, and then 2 centimeter. So this is how it goes. So we will now measure the wavelength of a wave which is at a particular frequency. I have set the frequency at 2 Hertz, and the distance between the crest of the wave which is produced, which is at a frequency of 2 Hertz, can be measured by keeping the ruler here at the top. So from this point to the another crest, the total distance, as you can see, is 3.2, since the value of one small division on this scale is 0.2 centimeter. So here it is 3, and this is the point at which the second crest is there. So this is 3.2 centimeter. So for frequency of the value 2 Hertz, the wavelength of the wave which is created is 3.2 centimeter. So now when we know the wavelength and the frequency both, we can easily calculate the wave velocity. So the next step is to calculate the wave velocity of the wave. So the calculator is right here. The frequency value is 2 Hertz and wavelength is 3.2 centimeter. The formula for calculating wave velocity is frequency into wavelength. Now that means 2 multiplied by the wavelength. Wavelength is in centimeter while frequency is in Hertz. Hertz is the SI unit of frequency. So in order to calculate wave velocity, we must convert the centimeter value in meter. So 1 centimeter is equal to 1 upon 100 meter. That means 3.2 centimeter will be 0.032. So on multiplying both these numbers, you get wave velocity as 0.064 meter per second. So that means under the given situations, the wave velocity of this particular wave is 0.064 centimeter. Just note down this value. The frequency of the wave is now halved, which is 1 Hertz. Now let's see what happens. This is the normal speed of the wave, and you can obviously see that the number of waves per second are lesser than the previous one, and therefore the wavelength should be longer. So the next step is to measure the wavelength. For this, I will pause the simulation and measure the wavelength with the help of rulers. I have now paused it again, and this is one complete wave, and with the help of this ruler I will now measure the wavelength by measuring the distance between two troughs. So I'm putting the scale, adjusting the scale properly. Now you can see the first trough is at this point and the second one is over here at this point roughly, right? So what is the distance between two troughs? It is the wavelength. So right now it can be 6.4. It is somewhere roughly, it is lying somewhere over here. So the wavelength of the wave right now it is 6.4 centimeter. So if you remember, when the frequency of the wave was 2 Hz, then the wavelength came out to be 3.2 centimeter. And now when you have half the frequency, the wavelength got doubled, which is 6.4. So let's see how much is the wave velocity. The frequency is 1 Hertz multiplied by the wavelength, which is 6.4 centimeter. So in meter, it will be 0.064. 0.064. So when you multiply these two, you get wave velocity, which is 0.064 meter per second. This is same as the previous one. That means even on changing the frequency, there is no change in the wave velocity. From all the discussions that we have done so far, we can conclude now that the frequency and wavelength of a wave bear an inverse relationship. That means if frequency becomes double, the wavelength will be halved than the previous value. So therefore, we can say that frequency and wavelength are inversely related to each other. Now, wave velocity is the product of frequency and wavelength. So the effect on one is being countered by the inverse effect on the other variable. Therefore, doubling the frequency means halving the wavelength, and so that it would make the wave velocity constant. Now, this is the wave at a normal speed when it is having frequency 1 Hertz. So on a very high frequency, if I increase the frequency of the wave very high, that means it is making many waves per second. And now if I suddenly slow up down and I am now speeding it again and then slowing it down, you would notice that the speed at which these crests are traveling does not change. Kindly observe carefully. Okay, the speed is not changing even if I am changing the frequency. So velocity of the wave is independent of frequency and wavelength, and this we have seen in the calculations. Even though it is suggested in the equation that wave velocity is the product of frequency and wavelength. There are other factors on which wave velocity depends upon, about which we shall study later. The animation here shows two longitudinal waves with two different frequencies but traveling with the same velocity. It can be seen that the wavelength is halved when the frequency is doubled, and the reason is frequency is inversely proportional to the wavelength. Kindly observe this animation carefully.
Through this simulation, you will be able to understand the concept of amplitude. In the amplitude slider, you can read the value to be 0. But if I slowly increase the amplitude, you can very well see that the transverse wave has been created. On increasing the amplitude, the vertical height of the wave, that means the size of the wave, has also increased, and on further increasing, this vertical height or the size of the wave is increasing. I hope you are able to understand clearly the meaning of the term amplitude. On reducing the amplitude, again the size of the wave has decreased. Now if I want to measure the amplitude of the wave, then I will pause this video and enable the ruler. We measure amplitude from the baseline to the maximum height, which is the crest. So I have adjusted the ruler here, and as you can read here that the amplitude is 1.02 centimeter here on this slider. So when you will look at the ruler, it denotes that this vertical height is almost 1 centimeter. 0.02 centimeter cannot be measured in this ruler because I have told you the least count of this ruler is 0.2 centimeter. So it won't be able to measure 1.02 centimeter. So you can see clearly the height, that means the amplitude or the maximum displacement from the baseline is nearly 1 centimeter or 1.2 centimeter in specific. So that is how we measure amplitude of the wave.